Okay, so now we're in section 2 of chapter 6, and in section 2 we're going to be solving equations, trig equations again, and these will be a little bit more complicated. Each will have a unique new approach to it, so please watch as we go through them, but we'll follow the same general pattern that we set up in the first section. So if you look at example 1 here, you'll see that we're in radians, and we're still restricted to one rotation, and that will change in section 3. So pretty soon we'll be doing infinite rotations. Well, what's unique in this problem is that we can see at the very start that we have a cosine x in the denominator. Since it's in the denominator, we can be assured that the cosine x is not equal to 0, and that's because we're not allowed to divide by 0 in mathematics. That's not possible. And that opens up an approach that we can't use normally. In this case, we can multiply both sides of this equation by cosine x to eliminate that fraction. Ordinarily, you cannot multiply by a variable because multiplying both sides by 0 is not allowed. It doesn't keep the equality intact. But here we know cosine x cannot be 0, so we will multiply both sides by cosine x. Again, the only time you can use this approach is when you know from the start that the variable you're multiplying by cannot equal 0, which we do know because it's in a denominator. On the left side, that would give us 2 cosine squared x minus cosine x, and on the right side, the cosine would cancel, leaving 1. This is a quadratic equation, so we'll have to get 0 on one side in order to solve it. We'll subtract 1, 2 cosine squared x minus cosine x minus 1 equals 0. This one does factor. In the front positions, we'll use a 2 cosine x and a cosine x. In the back position, we'll have to use 1 and 1, and to get our negative in the center, we'll need a negative there and a positive there. We'll set each of these two factors equal to 0. To isolate the cosine in the left one, we'll subtract 1 and divide by 2. That will give us cosine x equals negative 1 over 2. In the second one, we'll just add 1. Cosine x equals 1. The first one happens to have a reference angle. Cosine is equal to 1/2 for 60 degrees, so in radians that would be pi over 3. The cosine here is negative, so that means we're working with quadrants 2 and 3. In quadrant 2, we would have to go a full pi, which would be 3 pi over 3, and then 1 pi over 3 is subtracted from it. So in quadrant 2, we'll get x equals 2 pi over 3. In quadrant 3, we'll have to go again a full pi, but this time we'll have to go 1 additional pi over 3, so we'll have to add a pi over 3. So the x will be equal to 4 pi over 3. Now the other equation is not a reference angle problem. That's a quadrantal problem. So quadrantal means we're going to be thinking of the unit circle. And since cosine of, sorry about that, since cosine of theta is defined to be x over r, we'll be looking for the quadrantal angle, the one on the coordinate axes, where the x is equal to 1. And that occurs right here at 1, 0. So that would correspond to x equals 0 radians. The first problem, therefore, had 3 solutions. Let's take a look at the second example. Now, the second example, you can see that we're in degrees this time. We're still one rotation. It does tell us we're going to be rounding to the nearest tenth of a degree, so that usually indicates to you that it's not going to be a reference angle, 30, 45, or 60, and it's not going to be quadrantal. It's going to be one where we're going to have to use an inverse trig function. Now, we've done that before, so that's not what's new here. What is new is we have two different trig functions. If you have two different trig functions, you need to use one of three approaches. The first approach you should look for is, can you factor to separate them? And that usually requires you to factor out a greatest common factor. In this case, we do not have a greatest common factor we can take out. The second approach you should look for is, can you use one of the trig identities that you've learned in an earlier chapter to rewrite all of the trig identities, or the trig functions rather, in terms of the same trig function? Well, we don't have a trig identity that will change a sine to a cosine or a cosine to a sine, so we can't use that approach either. The third approach, and the one we least want to use but sometimes have to, is we'll separate them, putting all of one trig function on one side and all of the other trig function on the other side, and then we'll square both sides of the equations. Sometimes that will open up an identity that will work. Now, the reason we don't want to use this unless we have to is, when you square both sides of an equation, it can introduce extraneous solutions, as you learned back in Algebra 2 when you solved radical equations. So we will have to check our answers at the end to see if they're valid answers to the original problem. So to begin with, we have to separate them. I'll separate these by subtracting the square root of 2 cosine theta on both sides. And that will leave me with sine of theta on the left and negative square root of 2 cosine of theta on the right. And now we're going to square both sides. Now, that's going to necessitate we check at the end. On the left side, we'll have sine squared of theta. On the right side, squaring a negative square root of 2 just becomes 2, and then cosine squared theta. Well, at this point, we still have two different trig functions, but we can use the Pythagorean identity to rewrite all of them in terms of the same trig function. And I'm going to rewrite everything in terms of sine. So I'll have sine squared theta equals 2 times 1 minus sine squared theta. I'll distribute the 2. Sine squared theta equals 2 minus 2 sine squared theta. And now I'm going to move all the sines to one side. I'll accomplish that by adding 2 sine squared to both sides. So that will give me 3 sine squared theta equals 2. I'll divide by 3. I get sine squared theta equals 2/3. And now I have to get it down so it's just sine. And that means I'm going to take the square root of both sides. So the sine of theta is equal to plus or minus, because when you take a square root, there's two possibilities, positive and negative, the square root of 2/3. Now, this definitely is not one of our reference angles 30, 45, or 60, and it's not quadrantal. So in order to find our reference angle here, I'll have to use inverse sine, and then square root of 2/3. So for my reference angle, let me take my calculator. I get 54.7 to the nearest tenth. Because we have a plus and a minus, that opens up all four quadrants to us. So we have a possible quadrant 1 answer, a possible quadrant 2 answer, a possible quadrant 3 answer, and a possible quadrant 4 answer. Now, the quadrant 1 answer would have been our reference angle. So that would have been theta equals 54.7. I'm not going to box that yet, and I'll come back and tell you why in just a moment, or remind you of it. In quadrant 2, I would have had to take 180 minus 54.7. That gives me 125.3. In quadrant 3, I would have had to take 180 plus 54.7. And that's 234.7. And in quadrant 4, I would have had to take 360 minus 54.7. 305.3. Now, all of these are potential answers to our original equation, but some could be extraneous. So what we have to do is we have to check in the original. And the original, once again, was sine theta plus square root of 2 cosine theta equals 0. Now, we'll check that by typing them into our calculator, but we can save some time here. In quadrant 1, for instance, in quadrant 1, both sine and cosine are positive. So there's no possible way I can add two positive numbers and get 0. That means that the quadrant 1 angle must be extraneous. In quadrant 2, in quadrant 2, the sine is still positive, but the cosine is negative. When I type that one in, that one checks out fine. In quadrant 3, both sine and cosine are negative. There's no way I can add two negatives and get 0. So this one, once again, quadrant 3 comes out to be extraneous. Quadrant 4, this time sine's negative and cosine's positive, and that one, when I type it in my calculator, does check out. So when you square both sides of an equation, be sure you go back and check them in the original to make sure they're true. And the ones that are your true solutions must be boxed, and the ones that aren't cannot be boxed. So please make sure you pay close attention to that one. Now, there are only 4 examples, so let's get on with the last 2. This problem. When you look at this problem, it has only sine in it, and we're working in degrees. And we're still down to 1 rotation. And it's a quadratic. But it's a quadratic where the leading coefficient is negative. So what I would recommend is you first divide everything by -1, and that should make it a little easier to factor if it's going to factor. If I divide by -1, I have 2 sine squared theta minus 3 sine theta plus 1 equals 0. And then this one, I believe, does factor. 2 sine squared would factor into 2 sine theta and sine theta. 1, the only choices are 1 and 1. To get a -3 in the middle, both will have to be negative. We'll set each of those two factors equal to 0. So 2 sine theta minus 1 equals 0. Sine theta minus 1 equals 0. To isolate the sine in the left one, I'll add 1 and divide by 2. Sine theta equals 1/2. In the second one, the right one, I'll just add 1. Sine theta equals 1. Sine theta equals 1/2. That one has a reference angle. We're in degrees. The reference angle in degrees, where the sine is equal to 1/2, is 30 degrees. We have a positive sine. Positive sine happens in quadrants 1 and 2. Quadrant 1 is the same as the reference angle, so theta will be equal to 30 degrees. Quadrant 2, I have to take 180 degrees and subtract 30 degrees. So in quadrant 2, I get 150 degrees. You'll notice I boxed those immediately, and that's because since we didn't square both sides of the equation, we don't have to worry about checking at the end. Sine theta equals 1. That one's going to be quadrantal. And since sine is equal to y over r, we're looking for the place on the unit circle here where the y is 1. And that happens up there at the top. So that would correspond to 90 degrees. Now that one went much smoother. And the only part that was unique there was when you look at it, it was easier to divide everything by -1 because the leading coefficient was negative to begin with. Let's get to your last example for this lesson. And when you look at this last example, you'll notice that once again we have two different trig functions. We are in radians again. Still one rotation. And we have two different trig functions, but this time I think it is going to be possible to use a trig identity to rewrite everything in terms of the same trig function. The cosine squared here, we can use the Pythagorean identity to rewrite that in terms of sine. It would become 1 minus sine squared. We'll distribute the 4. That will give me 4 minus 4 sine squared x plus 4 sine x minus 5 equals 0. Combining like terms, we'll have -4 sine squared x plus 4 sine x minus 1 equals 0. The leading coefficient here is negative, so I'll divide everything by -1. 4 sine squared x minus 4 sine x plus 1 equals 0. And this one, once again, does factor. This time, to factor the 4 sine squared x, I'm going to choose 2 sine x and 2 sine x. Back ones are 1 and 1. To get a negative, I need negative and negative. Since both factors are the same, they're both going to yield the same solutions, so we don't have to set both of them equal to 0. That would just be repetition. Isolating the sign, I get sine of x equals positive 1/2. We just had one like this. We know that this is a reference angle. This time we're in radians, so rather than 30 degrees, we'll use pi over 6. The sign is positive, so we remember that's quadrant 1 and quadrant 2. Quadrant 1 will be the same as the reference angle, so that's going to be pi over 6. Quadrant 2, well, that's like taking a full pi, which would be 6 pi over 6, and then taking away 1 pi over 6. 6 pi over 6 minus 1 pi over 6 means our quadrant 2 answer is 5 pi over 6. You'll notice once again I didn't have to check, so I boxed them immediately. Your suggested problems are down below, and you'll notice that we skipped a few problems, and that's because those required identities from Chapter 5, which we did not cover this spring. Good luck on this. If you have questions, remember we have